moving on in our kinetics unit, we are looking at concentration and chemical rate. We realize that most chemical reactions are indeed reversible. If I think about the collision theory, initially at time 0, I only have reactants involved. There are no products yet made, so only the collisions that are occurring are from the reactants. But as time goes by and products are being made, they can indeed collide with one another. And if the orientation in space and with enough kinetic energy, they can break bonds and form new bonds, going back to the original reactants. When we say that reactions are reversible, we're simply reminding ourselves that if A plus B collides to make AB, AB compounds can collide with one another and break those bonds. So if we have A plus B to make AB, AB compounds can collide with one anher. At time 0, however, the initial concentrations, we only have reactants going on. There are no products yet. So the earlier the reaction rate is measured, the more dependent those rates are on the initial amount of reactants. If I let too much time go by, I start to interfere with the rate of the reaction by actually measuring a reverse process. So we call this the initial rate method. This method, called initial rate method, measures the concentrations at time 0 of the reactants as soon as they are mixed. If we know the concentrations of the initial amount of reactants and measure them several times at varied concentrations, we start to get insight with how the concentration is affecting the rate. So this method, called initial rate method, measures this concentration several different times. So we probably run 2 or 3, sometimes 4 different experiments by varying the initial concentrations of the reactants, and we start to generate data tables. If I started with 0.1 molar of a reactant, how fast does it go if I double the concentration? What have I done to the reaction rate? Those initial concentrations of the reactants then get varied, and we start to generate a data table. Rate laws show how the rate depends on the concentrations of the reactants. It does not, I repeat, does not have anything to do with the stoichiometry. The rate expression has to deal with the stoichiometry. Rate laws do not depend on the stoichiometry. You have to determine via experiment, and they're based on initial concentrations and reaction speed or kinetics. So the only way to determine a rate law is not from a balanced equation, but from experimental data. If this reaction, and again, we wrote that up above if it looks familiar, dinitrogen pentoxide decomposes into NO2 and O2, and if the reverse reaction does not play a role, notice it's only a forward arrow. You can find the rate will only depend on the concentration of the reactants. So we write what's called a rate law. The rate is equal to K, which will be the rate law constant, times the concentration of N2O5. And notice that's the reactant raised to some power, and we'll call it N. It's not squared. It has nothing to do with the coefficient. It has to be experimentally determined. And I'll explain how this is called a rate law. Rate law is equal to K, a constant, times the concentration of our reactant raised to some power N. This K is a rate law constant, and it depends on temperature and the solvent used. And N is called the order of the reactant. It's usually a positive integer, and for the scope of this class, we'll talk about first order and second order. So rate is equal to K, that's a rate constant, times the concentration of the reactant. We do not consider the product in an initial rate method because we're assuming it's at time 0, and that only has to deal with our reactants. Let's dive a little more into that. What we have here is generating two lists that we could do in our calculator. On this side, we have time. As time goes by, we're measuring the disappearance of our reactant. So at time 0, we have 1 molar. After 200 seconds, we have 0.88. 400 seconds, we have points down to 0.78, and so forth. If we graph this data, it looks like this kind of slope. And again, we could do this on our calculator, list, we would generate a graph, and at this point, we just take a look at this one that's been generated. I want to find two convenient points to find how varying the concentration affects the overall rate. So the first one I noticed is an intersection here at about 0.8 and 400. Now, if we cut that concentration in half to 0.4, and that's going to be at about 0.4, about 1600. By looking at these 2 points, we can see how varying the concentration affects the overall rate. So let's assume that we find the tangent to this point here at 0.8 molar, and at that instantaneous point, we took that information, and I'll show you how to do that. It's a little bit of calculus. We'll do that in a minute. But if we did that instantaneous point over 400 seconds, or it'd be a negative 400, we would get a rate of 5.926 times 10 to the negative 4th molarity per second. The same was also done at 0.4 molarity. Again, we found the tangent to this graphically, and we took that information and divided it by the change in time, and that was given to us as 2.963 times 10 to the negative 4th molarity per second. So if we look at these a little bit closer, and we want to know, how does the concentration affect the rate of our reaction? So we generate these lists in a data table. List 1 represented the time going down, and list 2 represented the concentration going down. We graph that information of concentration versus time, and we solve just convenient points. 0.8 and 0.4 were selected because they're half of one another. We solve to find the instantaneous rate by finding the tangent of the line. That's a calculus move. I'll show you in a bit. We did the same thing. So at 0.8 and 0.4, we found the instantaneous slope. And all we're doing there is saying at that instant in time, we have a rate of molarity per second. So if we stand back and say, how did the rate become affected by changing the concentration? In my head, if I were trying to compare these two numbers, I want to look like this. Remember, this concentration is at 0.4, and this concentration is at 0.8. So 0.4 to 0.8 is double. That is doubling. 0.4 to 0.8 is doubling. We know 10 to the negative 4th and 10 to the negative 4th are the same, so let's pretend that those are gone. 2.963 in my head is really close to 3. I'm just going to put that there. 5.926 is really close to 6. So if I look at these two numbers, 3 to 6 is doubling. 0.4 to 0.8 is doubling. So when I double the concentration, my rate is doubled. So since the rate at twice the concentration is twice as fast as the rate law must be to the first order. So we'd write that as rate is equal to the constant times the concentration of N2O5 to the first order with respect to our reactant. This had nothing to do with the stoichiometry. The only way to determine order is to run the experiment. So now we can go back to our notepad. Sorry you didn't have the PowerPoint slides. But through the process of graphing, we said that 0.8 molar, the rate was determined through an instantaneous rate method to be 5.926 times 10 to the negative fourth molarity per second. And at 0.4 molar, we found the rate to be 2.963 times 10 to the negative fourth molarity per second. My logic was to disregard the times 10 to the negative fourth when comparing these. It'd be like comparing 100 to 200. They both have two zeros, so we could compare just 1 to 2, and we could say that it's doubled. That's what I was going with. So I just took this off, and I was comparing about 3 to about 6. So we doubled the concentration. We could see that the rate did the same thing. Think of it this way. If I doubled the concentration, what power do I raise that number to double the rate? And so in this case, 2 raised to the first power is 2. This must be a first order reaction with respect to N2O5. And like we showed, we would write that as K concentration N2O5 raised to the first order. On a side note, the other reaction that we would study, we would say we'd study zero order, first order, or second order. Suppose we doubled the concentration and the rate quadrupled. The concentration would go 4 times as fast. What order with respect to the reactant would this be? Well, 2 to the second power would give us 4, so that would be to the second order. And if we were to look at zero order, and that just means there's no effect. If I double the concentration or triple the concentration or whatever, there's no effect on the rate. It just drops out of the reaction altogether. 2 to the 0 power equals no effect. And typically that will happen for catalysts since they're not reactants or products. So with zero order reaction, no matter what we do to that concentration, I see the reaction rate not doing anything. It just stays the same rate overall as if I hadn't changed it. We call that a zero order. So again, in this case, we say that this reaction is first order. We double the concentration and our rate doubled. That is a first order. If we doubled the concentration and our rate quadrupled, that would be a second order. If we doubled the concentration and there was no effect on the rate, that is a zero order. The only way to determine order is to run the experiment. So if we look at our general terms, if we have reactant A plus B going to C plus D, the rate law comes from reactants only. In the initial rate method, there are no products. They're not considered. But in this equation, we would say that rate is equal to K times the concentration of reactant A raised to the power of, we're not going to say little a, again, it has nothing to do with stoichiometry. We're going to use these other little letters. We'll call it to the power of m, what order of m, times the concentration of B raised to the order of, we'll say n. Now, so these little letters, we tend to not use the letter O because it can be confused with the number 0 to represent a 0 order. So using these, we can describe the order of the reactant with respect to the concentrations of A and B. So those exponents, M and N, are called reaction orders. If exponent is 1, the rate is first order with respect to that reactant. If the exponent is 2, the rate is second order with respect to that reactant. The overall reaction order is the sum, so we're going to add together the orders with respect to each reactant. So again, the exponents in a rate law indicate how the rate is affected by the concentration of each reactant. They must be experimentally determined. It has nothing to do with the stoichiometry. We also saw that if the rate doubles when concentration doubles, or if the rate triples when the concentration triples, that is a first order reaction. If the rate follows directly, it's a first order. We have a second order reaction. If you double the concentration of a reactant, the rate will quadruple. So if I were to say if I doubled the concentration, the rate quadrupled, that would be second order. 2 squared would give me 4. Or let's say I tripled the concentration, and that caused the rate to increase 9-fold. So 3, if I tripled the concentration and my rate went to 9, that means 3 squared is 9, so that's the second order. Squaring the concentration to find the effective reaction rate. And then we have 0 order, where the concentration has no effect on the rate. So it does not play a key role in the reaction mechanism. Let's look at this reaction. I've got 2NO plus 2H2. Those are my reactants. Create NO and 2H2O. So here is our rate. It tells me K, and then the concentration of NO to the second order times concentration of H2. So again, remember, we're not looking at stoichiometry here. Even though there is a 2 there and a 2 there, it is not related because there is a 2 also in front of hydrogen and a 1 there. So what are the reaction orders in this rate law? Well, if I look at respect to NO, we can see that NO is second order. And if I look at H2, is first order. And then if I look at overall, remember we use the sum of them. 2 plus 1 is third order overall. Let's look at this one. Does doubling the concentration of NO have the same effect on rate at which doubling the concentration of H2? Well, let's look at that. Our NO is a second order. So if I doubled, so 2 times 2 squared, that would quadruple my rate. And if I look at H2, which is to the first order, so if I doubled my rate and it's to a first order, 2 to the first power is going to give me double my concentration. So no, it does not have the same effect on rate. The exponents are different. giving us different effects. Let's look at some sample data. It wants us to determine the order of this experimental data. So I've got hydrogen peroxide plus 3 iodides plus 2 hydrogen ions that react to form I3 to a -1 and a couple of waters. So we want to determine the rate law. Notice that I'm given H2O2 concentrations, I'm given initial iodide concentrations, and I'm not given any hydrogen. It says no data given for hydrogen ion means we're assuming the order is 0. Well, let's just start with our skeleton rate and write down that we know that we have our rate law constant times the concentration of H2O2 raised to, we don't know what rate law or what rate order yet, times I minus, concentration of I minus 2, we don't know that order, and then times the concentration of H plus. And that, again, we assume is to the 0 order, it said. So you could leave it out, or you can just write it to the 0 order. So let's look at this, assuming that this is trial 1, this is trial 2, this is trial 3. So we're given these concentrations, and rates. So one thing I want to look at is we've got 6.9 times 10 to the -4, 3.4 times 10 to the -4. So we can look at those on an even playing field, but this is to the -3. I would suggest making sure that all of your rates are in similar notation. So if we want this to be to the -4, this would be 14 times 10 to the -4. So I'm going to cross this off just so that we can compare a little bit easier. So then what I like to do is look at, for example, trial 1 and trial 2. Let's compare these two, where we can see that my iodide concentration stayed the same. So let's look at what happens to my H2O2. If I go from 0.1 to 0.05, so we know that going from 5 to 10 is doubling that. So I can show that 0.1, this is for concentration of H2O2. 0.1 over 0.05 is doubling. So when I double, what is happening to my rate? And I can see that, again, if I compare like to like, if I took 3.4 and I doubled it, just like I did 0.05 and doubled it to get 0.10, I would get 6.8. And we see that this is 6.9. So with experimental data, it's never going to be perfect, but we can see that that is doubled. So when I double my concentration of H2O2 and I stays the same, we can see that my rate also doubled. So we'd say that this is to the first order with respect to the peroxide. And again, it's important to hold one reactant constant while we look at what's happening to the other. Now, for our second one, to find the order for iodide, I want to keep my peroxide constant. So let's look at trial 1 and trial 3, where my peroxide is constant, and then see how that compares with our iodide. So as H2O2 is constant, my iodide we can see doubles, going from 0.1 to 0.2. So let's look at what happens to that rate going from 6.9 times 10 to the -4 to 1.4 times 10 to the -3, or 14 times 10 to the -4. So we're going from about 7 to about 14. And again, you could do, if you didn't like changing the decimals, you could do 1.4 times 10 to the -3 divided by 6.9 times 10 to the -4, and you would get really close to 2. So we can see that that is first order with respect to iodide. When I double the concentration, going from 0.10 to 0.20, so I double the concentration and my rate doubles, so that is a first order reaction with respect to the iodide. Now let's dive into more about K, looking at that constant. We can solve for that rate constant K and solve for its units. So going back to look at our data, for no other reason that just because it's written first, I like to use the first trial. We could use any trials and we would get the same answer for K. So we're just going to plug into our rate that we wrote, our skeleton, with the correct orders and solve for K. So our rate, so I'm going to use the 6.9 times 10 to the negative 4. And that's molarity per minute. Usually it's molarities per second, but in this case, molarity per minute is equal to K times the concentration of H2O2, and in trial 1, it's 0.1. And again, it's to the order of 1, times the concentration of iodine, which in this case, also 0.1, raised to the power of 1, times the concentration of hydrogen, which we're not given. We're assuming, and it's to the 0 power, so that's negligible. So now we just need to solve for K. 0.1 to the power of 1, I mean, you can just do 0.1 to the 1 power is 0.1. So 0.1 times 0.1, 0.01. So we're going to divide both sides by 0.01. So 6.9 times 10 to the negative 4th divided by 0.01. We get 0.069. Or we can write this as 6.9 times 10 to the negative 2. So our K is equal to 6.9 times 10 to the negative 2. Now, when we get to units, we have, this is our concentration, 6.9 times 10 to the negative 2. So we need to write M for molarity, concentration, 1 minus the total order. So we need to do 1 minus, the total order is 0 plus 1 plus 1, so 2. 1 minus 2 is equal to negative 1. So we're going to do our concentration of molarity to the negative 1 divided by time. And our time is minutes. And when we write divided by, that's also to the negative 1. So in this case, since M is to the negative 1, that also means divided by, so we could just do molarity minutes. This is the same as this. Let's talk about that one more time. I took trial number 1 and plugged into my rate expression here. I could have done trial number 2. I could have said 3.4 times 10 to the negative 4 is equal to K times 0.05 to the 1 times 0.1 to the 1. Solved it, I would have gotten the same answer for K, 6.9 times 10 to the negative 2. To get my units, concentration, M, to the 1 minus my total order, I added up my total order. 1 plus 1 is 2, so 1 minus 2 to get negative 1. So molarity to negative 1, which means it's the inverse of molarity, so 1 over M, and then divided by time, that means, so divided by minutes that we're given. Pause the video here and look at this next example. Take a really good look to see if you can find the rate law. How does changing the concentration of A and B affect the rate? Are they first order? Are they second order? Work it out. And start the video again when you're ready. Well, let's see what we got here. First thing I noticed here was that when A is staying the same here, let's look and see what B is doing. So here I can see I went from 0.8 to 0.4. So I'm just going to do 0.8 divided by 0.4, which we should get 2, but let's just double check. 0.8 divided by 0.4. All right. So concentration has doubled. Oh, no. Yes, concentration has doubled here. So let's see what happened to the rate. So I'm going to do 14,460. This is molarity per second. And divided by 3600. 460 divided by 3600. And that's about 4. So when I'm writing my rate law, I'm going to say that my rate is equal to, I know I'm going to have my A to some power and B to some power. And when I'm looking at B here, we need to figure out what that power is. So 2 to the what power, when I double my concentration, my rate goes to 4. So 2 to the second power, 2 squared is 4. So when I double my concentration, my rate is quadrupled. So B is to my second order. Now let's look at A. Now, when we're looking at A with respect to A, there's never a time where B is staying the same. So we're just going to pick trial 1 to 2, just for the heck of it, because when we're doubling B, that's easier than looking at 0.2 to 0.8. So we're going to compare these two for A. So let's look at first what our rate is doing. We're going from 3,600 to 300. So let's find out what that difference is. 3,600 divided by 300 gives me 12. So this is telling me that my reaction is going 12 times as fast from trial 1, this to this one. But we also know that both of these reactants are influencing that. But we can factor out knowing that B is second order. Here's what I mean by that. If we look at B, trial 1 and 2, we know that its concentration doubled. So we just did 3,600 minus 300 to get 12, quadruple the rate, or 12 times the rate. But if we look at B specifically, we want to factor this out. Its concentration went from 0.4, or 0.2 to 0.4. So figure that out. We know that that is 2. Its concentration doubled. And we know that it is a second order. So its reaction rate is 4 to the 4th. So we can take this and factor that out of my total. Because the factor of 4 is coming from the influence of B. We want to get B out of the equation. So we can take B's influence of 4 because we know that we doubled the concentration, which gives us a quadruple rate. We'll take that 4 out of the 12 so that we can just get A by itself. And by doing that, 12 divided by 4, we get 3. And this 3 must be coming from A. Okay, so now let's look at what's happening to A from trial 1 to trial 2. And we can see that its concentration went from 0.10 to 0.3. So if we did 0.3 divided by 0.10, we get 3. All right, so if the concentration is tripled, what order does it need to be to triple the rate? And we can see that this has got to be an order of 1. We started with comparing trials 2 to 3 because we were able to hold A constant. So we were only able to just look at B. We were able to see that going from 0.4 to 0.8 doubled my concentration. And by doubling the concentration, we saw that it quadrupled the rate. That gave us an order of 2 with respect to B. Trying to find out what A is, though, we were never in a spot where B was held constant. So we just looked at trial 1 and 2 and looked at what happened to the rate. 3,600 divided by 300 gave us 12. And then we wanted to factor out B. We know B is second order. So we can see here that B doubled. We know that its concentration doubles, that its rate is quadruple. So we factored out 4. We factored B out of the equation to get 3, which is when telling us that A's rate tripled when its concentration tripled. So therefore, that's got to be an order of 1 with respect to A. Now let's find K with units. So I'm just going to use trial 1 just because it's listed first, but you can use any trial that you'd like to, as long as you take the rate, which if you're going to use trial 3, you use 14,460. I'm just going to use trial 1, so my rate is 300. And again, this is molarity per second here is equal to K, oops, I forgot to have my K up here, K times A to the 1, B to the second. So K times the concentration of A, which would be 0.10, raised to the 1. I can just put parentheses around here if I'm not looking at concentration of A, times B, which is 0.20 to the second power. Now I'm going to use my calculator here and do 0.1 to the 1 times 0.2 to the 2, and then I'm going to do 300 divided by the answer to get K by itself. Should get 75,000. So K is equal to 75,000 M to the, now remember with our units, I'm going to do 1 minus my total order, so 2 plus 1 is 3. So 1 minus 3 is negative 2. So my units would be M, negative 2. And then seconds, that's what my time is in, negative 1, because it's per time. So we would express that as seconds negative 1. Why don't you try to attempt this next one? The data table is on the back side of this page, looking at these concentrations and rates for 4 different trials. So see if you can set this one up. Well, let's look and see what we've got. We've got 4 trials. And on the page before, we were told our rate is equal to our constant times the concentration of BrO3 minus to an order yet to be determined times Br minus to an order yet to be determined. And this time we have all 3 reactants, hydrogen H plus, to be determined. So now I'm going to stare down and try to find where 2 reactants hold the same from one trial to another, and only one is changing. Then we can single that one out. And it's not too difficult to see that in trial 1 and 2, H plus stays the same, Br minus stays the same, and only this guy is changing. And we can see that it doubles from 0.10 to 0.20. So my concentration of BrO3, I can see that if I did 0.2 divided by 0.1, I get 2. So concentration doubles. Let's see what happens with our rate. So I'm going to do 1.6 times 10 to the negative 3 divided by 8.0 times 10 to the negative 4. So let's see what happens with that. 1.6 times 10 to the negative 3 divided by 8.0 times 10 to the negative 4. And we see that it doubles. So again, setting that up, this is for BrO3. When concentration doubles and my rate doubles, that must be to the order of 1. So I'm going to put a 1 in down here. Okay, so we've got BrO3 out. I'm just going to cross it off so we know we're done with him. First order with respect to BrO3. Now let's see if we can find one where these two guys hold constant for a from one trial to another, and let's just find bromine. Okay, well, how about this one? Going from 2 to 3, BrO3 stays the same, and H plus stays the same, but we can see that Br minus is doubling, going from 0.1 to 0.2. So let's show our Br minus problems over here. 0.2 to 0.1, that's us doubling the molarity. Let's see what happens with our rate. So we're going to do 3.2 times 10 to the negative 3 divided by 1.6 times 10 to the negative 3. And hopefully if you were able to see this, 3.2 divided by 1.6 is going to be 2, but we could plug it into our calculator, we would get the same thing. So double the molarity, double the rate. That means that this has got to be first order with respect to bromide. So that is also a first order. All right, our last, I'm going to cross off bromine now. Now we need to find the hydrogen. What order is hydrogen? So we need to see, are there any times when the bromide and the BrO3 stay the same from one trial to another and something with hydrogen changes? Well, just trying to look it out. From 2 to 3, BrO3 stays the same, but hydrogen is not. The only time that hydrogen is changing is going from 3 to 4, but this is changing and that's changing, so we can't just keep it alone, keep these the same, I mean. From 2 to 4, we see H plus changing. 2 to 4, oh good, this one stays the same. Oh, but 2 to 4, BrO3 is changing. What about 1 to 4? 1 to 4, BrO3 stays the same. 1 to 4, Br stays the same. 1 to 4, our hydrogen is doubling. Good, this is a good thing. So we're going to look at 0.2 to 0.1. We're doubling our concentration. So let's see what happens when we look at our rate. 3.2 times 10 to the negative 3 divided by 8.0 times 10 to the negative 4. 3.2 times 10 to the negative 3 divided by 8 times 10 to the negative 4. And that gives us 4. So if we are doubling our concentration and our rate is quadrupling, that means that this must be an order of 2 with respect to our hydrogen ion concentration. And on the page before, it asked us to solve for K. So for no other reason than it's listed first in trial 1, I'm going to use all of our trial 1 data to fill in for all of our information to solve for K. So our rate, 8.0 times 10 to the negative 4. And this is molarity per second is equal to K times our concentration of bromate in trial 1 was 0.1. And that's raised to the 1. Times bromide, also 0.1, raised to the power of 1, times our hydrogen, 0.1 raised to the power of 2. All right, so let's do some simplifying. I'm going to do 0.1 times 0.1 times 0.1 squared. And then I'm going to divide both sides by that to get k by itself. So 8 times 10 to the negative 4 divided by my answer that I just found. And I got my constant here, k is equal to 8. Now, remember to find our units. We take molarity and we're going to raise it to 1 minus the overall order. So I'm going to do 1 minus our overall order. Remember, our bromate was to the order of 1, bromide was to the order of 1, and hydrogen was to the order of 2. So 2 plus 1 is 4. 1 minus 4 is negative 3. So 8 molarity is to the negative 3. And then over time, and our time is in seconds here, so seconds raised to the negative 1. This would also be, if I wanted to write this out in fraction form, the same as writing 1 over molarity times molarity times molarity times seconds. This would be molarity cubed, but it's on the bottom part of a fraction, m times m times n, and then seconds to the negative 1 means over seconds. So these two units are equivalent to one another. You just tend to see it written more, it's just linearly this way. So m to the negative 3 is the same as saying 1 over m times m times m. And then seconds to the negative 1 would be the same as 1 over seconds.